So you're just trying to put this in your calculator in any nice way possible. You're going to say that n is equal to 9,000. E to the minus 0.2 times 5. And you get 3,451 approximately. Did you get that out of your calculator? Are you getting this out of your calculator? As I see people are typing away.
How would you enter that in the calculator?
Good
You
question.
enter the number first, then a negative, I think.
Given your calculators, I probably can't tell you too much, but we need to figure out a way. You got 9,380 times, and then you're looking for the E button.
So,
Oh, got it. Okay.
That's the E button, and now you want the E button to an exponent. That exponent happens to be minus 1. Are we finding out how to do this? Thank you.
okay, so,
That's the answer.
yeah.
3451. 3 plus times. Okay, you didn't put the E right away.
No, I
And then
multiply that.
this one. Okay.
Mhm. Yeah, I multiplied the exponent part out first, and then just, I don't know, that's easier for me.
Yeah, yeah. I understand.
Another question for you while you're waiting here, for people to sort of figure things out. What is n when t equals 0?
Oh, 5 times 10, so it's E to the power 1. So.
Raise e to the exponent 0, and what do you get? The same n as the n0, right? You find out that n is equal to 9,380 e to the minus 0.2 times 0 equal to 9,380 e to the minus 0. And the reason I bring this up is people are often afraid of exponents that are 0. But an exponent that is 0 is always 1. Actually, it's not always 1. The one case where it's not 1. 0 raised to the 0 is not 1. But other than that, one exception, when you see anything raised to the 0 power, it's going to be 1. And so, of course, you get 9,380. And what I'm also hoping that you recognize is why that character has that 0 there. That 0. This is, we write this as n0. Why is it as n0? Because that's what it is when t equals 0. The initial value. All right, time for something a tad more challenging. We've got to go the other way with this equation. I'm going to ask you, what is t when n has a certain value? Rewrite our equation. That is 80 e to the minus 0.2 t. That's your starting point. You're going to use this information and you're going to tell me what T is. So interesting.
We got lost here.
You got lost here?
Yes.
Is this this? Don't feel
So
bad.
why did you put the 9380 here? I thought we're going to use that.
That's my N0, same one I used
But we're
before.
calculating for 1 to 8.
This is in, this is not N0. So you do that. Now what you gonna do?
Okay, I know.
Phone a friend? Phone a friend, yes.
Or, yeah.
Google it, yes.
The problem is I don't.
You use the log or no? Yeah, I think you use log. I think that's it.
Okay.
You're gonna do the basic, and that's certainly fair, right?
Yeah.
All right, that's certainly fair. Now we got to deal with that exponent. How do we get the exponent out of the the variable out of the exponent side?
Log both sides.
Log both sides. Now you'll notice on your calculator you have 2 log buttons. Which log button do you use? The one that says LOG or the one that says LN?
LOG.
Either.
Yeah, it can actually use either, but the LN button is going to be the one that helps you out, makes life easier. Because LN is going to take care of E very nicely. So what you're going to do is you're going to do the LN, not log, of this side, divided by 9,380. And you're going to do the same thing to the other side, but this you're not going to put into your calculator. And the reason you're using this, it's called a natural log. The N here means natural log or log base E. And when you have LN and E working together, they undo each other.
Okay.
So what you get when you put an LN on an E
1.
is you get, not quite 1, but you get, well yes you do get 1. You get minus 0.2 T. In order to get the exponent, the variable out of the exponent, you do the ln of the E, and all that gives you is what was the exponent is now not the exponent anymore. Do you see how to solve for T from here on? So we're going to say that T is equal to 1 divided by negative 0.2 times the ln of 1,280. 9,380.
All that makes sense.
Yeah. Bracket there.
Where's that one?
And your answer is 9.96 approximately.
Here it is.
Rounding off to three digits there, 9.96.
I guess I like the lowest first. Versus what did he call this? What did he call this number? And of the other.
Yeah.
Think we got it?
No.
Not yet.
There you go. just enter your number first, huh? Hit L and do this.
Something to work on if you're having a little trouble. Since it sounds like most of you got it, I want to move on and we only have 10 minutes left. We need to get into this last topic that I wanted to get done today,
Okay,
which is graphing. And very simple, the way you did graphs when you were in algebra. And if you were asked to make a graph of y equals x over 2 and plot it on something that looked like that, you would say, how do you start graphing things like that? Yeah, just pick points and say, okay, let's make a table of points. Your most basic concept of graphing is to make a table of points. When x is 0, y is 0. When x is 1, y is 1/2. And when x is 2, y is equal to 1. And then you plot the points. There. Here. And when x is 2, y is 1. And then you connect them with a straight line. That would hopefully not surprise anybody. Excellent. Okay, so you probably don't find this, you would not find this reasonably interesting at all, but something that's happening to the numbers along here and the numbers along there. And this is so obvious you don't even know you're looking at it. You don't know you're looking at it until it's not there, and then you start scratching your head and say, what's going on here? Okay. If from 1 to 2 is 1 unit, last time you looked. From 2 to 3, also 1 unit. 3 to 4, also 1 unit. 1 to 2 is 1 unit. 2 to 3 is 1 unit. As you go from one point to the next point, you're always moving by 1 unit. And you never thought that they would bother to label this thing. This is called a linear scale. And because this graph has linear scales on both axes, it's called a linear graph. Move my y out of the way there. So now that you know that this is a linear graph, and that's what you're familiar with, there must be something that's not a linear graph. Right. And the two other characters that we have to play with are what is known as the log linear, or the linear log, and the log graph. So we have a log linear and we have a linear log, depending on which one is linear and which one is log, and we also have the log. And so I found a reasonable example, I think, here. This place called Interactive Math, or intmath.com. In their graph world, they have some things like this. And here is an example of a log graph. And what you're going to look for is the uneven distribution of the sublines. And the major lines, like the major unit lines, like from 1 to, on the previous graph it was 1 to 2. This graph it's 1 to 10. Okay, fair enough. That's 10 units. But the next one is 10 to 100. That's 90 units. And from 100 to 1,000, 900 units. So it doesn't go evenly, is the big story. And this one happens to be a log example. 0.1 to 1, and then from 1 to 10. So again, it's not even. What is evenly spaced are these black lines, and these black lines indicate powers of 10. That's the log nature of the graph. It goes by powers of 10 instead of being linear. And let's just see, given this graph, hope you can see it in the back row there, but if I looked for, say, this point right here, can you tell me what two numbers specify that point? This point on this graph right here. How do I read that point? 1.5 and 100. Huh?
3 and 100.
Keep it in mind while I try to do something here for a second. So I want to see if this will actually work.
I think you're right.
Red change.
Because that's the third line.
Yeah, like they're unevenly spaced, but there is 10 total lines.
Even though it looks like the middle.
Cool, I got it. All right, so I asked about this point here. Maybe I didn't blow it up even. That would be too cool, wouldn't it? Oh, we have technology.
I think it's 3.
All right. So I was asking about this point right there, and how do you read it? You say, well, okay, this number has, we need to label this, we'll call y, and we'll call this one x. For this point, we have a y value of
100.
Everybody's okay with that? Y value, if you're looking for the y value, you just read horizontally across until you get there. If you're looking for the x value, you just have to read down. Comes out close to that. What is that point there?
3.
3.
No.
The green grids are
3.
This is 1. We're sure. Yes, it says
Yes.
1. Okay. 2. This green one here is 3.
3.
4, 5, 6, 7, 8, 9. And this one looks like it's just a little bit short of 3. So let's call it 2.9. It's not 3, but it's close to 3. All right, let's do another one that's unambiguous in the other direction. We'll take something that lands on a green line, vertical green line. Anything. What's the best one to use here? This point, right here. Because we did something right close to it. What are the coordinates of that point right there?
Y equals 28.
27 and 2.
2.
So you got the 2 easy enough. That really is 2.
Yeah.
And then you have to read over
26.
25.
Yeah, 25.
25 would be a reasonable estimate. Yeah. You're not going to be able to exactly pick it off, but that's 20, that's 30, so somewhere in between 20 and 30. And you would say, in this case, x is equal to 2, y is equal to approximately 25. We'll put approximate signs there. Any major surprises on that? Takes a little bit of practice, but once you get used to it, it's not bad. Why do log plots exist? To torture you, of course, right? Oh yeah. This happened to a website, actually made a rather, I thought a rather comical example here. Frequency of word use, and this is of course in the English language. The top 3 words used in the English language are
The,
of, and.
and.
There you go, could have guessed. And if you scroll on down, they made a graph of this. Now, is this a linear or a log graph?
Long.
Linear.
Are your units evenly spaced as you're going along the horizontal and the vertical axes?
Yes.
Well, the vertical is different from the horizontal.